Alright, first three problems from last biweekly contest. Find valid pair of adjacent digits in string. We given a string S and we are told that we want a valid pair. So we want two adjacent digits in S such that the first is not equal to the second and each digit in the pair appears in S exactly as many times as its numeric value. So it's given it's a digit and we are told that in each pair every digit, both the digit needs to appear as many times as it is indicating, right? So if it's a 3 character, 3 means 3 number of times 3 must appear in S, which is happening. 2 number of times 2 must appear in S, which is happening. So this 2 3 is a valid string and we want to return the first string, first such adjacent pair that we encounter from left to right, and that's it. We return that, otherwise we return empty string. So straightforward, we can have a map. This will be of char comma end. We can also have a bucket count or something like that. For every character in S, we are going to increase the frequency in the map and start iterating from S dot till one less, because we are comparing the adjacent digits, so just one less so that we don't go out of bounds in the check. We get the character just so that it is more convenient. Let me call this ch1 instead, s of I plus 1. So if ch is not equal to ch1 and the frequency of ch is equal to the int version of ch minus 48, because or we can do it this way. And lastly, the same thing goes for ch1. Alright, if this is the case, then let me get a string answer which is initially empty, answer plus equal to ch plus ch1. Alright, and we return the answer here, otherwise return empty string. Let's see if this works. Oh, my bad. I think what we can do is do it this way so that this doesn't happen. Alright, so this is a linear time and space is also constant, because in frequency the character is the number of keys which is going to decide the size of the map, and it's at most going to be 26. So we can consider this constant space. Moving to the second problem, reschedule meetings for maximum free time 1. We are given an event time which is spanning from 0 to the event time. So there is a timeline, and in this timeline we have in between meetings starting from the start time and end time. So we have few meetings. So this is a vector, this is a vector. The index, the same index is going to correlate to the same corresponding meeting. All right. So what we mean is, if 1 and 2 is at 0th index, so the meeting starts from 1, ends at 2. And same thing goes for 3 to 5. So there is another meeting. All right. And we have a event time. And we have a k such that these are the many meetings that we can change in terms of we can just slide the meeting in between different gaps. All right, so this can be confusing, so let me get the marker out. So we can change k number of meetings at most, and we want to do it such that we have a largest or maximum amount of free time possible after rearranging the meetings, right? So what we can do is we can take an example, something like this. Suppose this is 0 and this is spanning till 15. Alright, and k is suppose something like 4. Alright, and we have a meeting starting at this point, this point, this point, this point, this point. Suppose this is at 1 to 2, this is 3 to 4, this is 5 to 6, this is 7 to 8, and this is 9 to 10. Alright. I'm sorry for the bad handwriting. I'm not used to using mouse as a writer. Alright, so these are the meetings, and we want to find what's the maximum gap that we can achieve continuously by switching k number of meetings, and the switch should happen in such a way that I'm not taking another meeting and reshuffling it. I'm just sliding it in the gaps if it is there. Otherwise, I can't. Right? So I can slide this particular meeting to starting from 0 to 2, sorry, 0 to 1, or I can slide it to 2 to 3, right? And same goes for all the other meetings. And I want to do it on k number of meetings at most. I can't do it more than that. And in that operations, I want to find the maximum number of continuous free time that I can achieve in the event. So I can't take the meeting and throw it outside the event. That's not possible. And lastly, yeah, I mean, these are a few of the things that we need to keep in mind. What we can do here is we can take a k window size such that we have k boxes inside, right? And that k boxes, suppose we are taking this, fixing it, taking this, fixing it, or you know what, let me make it better. Remove this, remove this, remove this, take this here, take this, create another line, right? This is ending at 15. Added few boxes, 11 to 12 and 13 to 14. You get the idea. So here, if I take a window fixing at this point, or more specifically fixing at we can do it either way. Suppose we fix it here, this end point and this starting point, right? So we have 4 boxes inside, and the gaps we can keep count of that. That is basically going to be 11 minus 2, and these durations are going to be shifted together so that I get a continuous space. So it's going to be 11 minus 2 minus the meeting duration, that's going to be 1 2 3 4 4 size of 1, so 4 into 1, 11 minus 2 minus 4, that's going to be 5, right? 5 is going to be the answer if we fix this, so that we can now take this sliding window, shift it to here, and do the same thing. Right? Now these are the boxes, and we are going to do the same thing eventually, just that we need to be careful about the cases such that the boundary cases, right? So this is going to be the first window from 0 till the, actually not even this, my bad, I'm sorry about that, this. So I have 4 boxes, and the 5th box's starting time is going to be my window. And similarly, the last boundary condition needs to be analyzed carefully. That's it. That's all we are going to do. So first, let's have a window indicated by the ith and jth pointer initially at 0. Let me get the size of the start or the number of meetings. Now let's get the meeting duration, because we are taking the window and sliding it. What we are keeping track of is the meeting duration, because we can always get the boundary, lower bound and upper bound, and get the gaps if we have the meeting duration. So now let's first, we need to get the boundary of k boxes, right? So let's get that, and then we can just shift both the pointers together in a different loop. So first I'll just get the window size as k. So we are going to be careful for the boundary condition, and we are going to continue as long as j is less than k. K is always going to be less than n or equal to n, so we don't need to worry about the out of bound scenario. So I'll keep track of the meeting duration. That's going to be end time. What is the meeting duration? It's going to be the end or the end time of a meeting minus the start time, right? And that's going to be j minus start time of j. I'm going to do a j plus plus. Let's get a free duration. That's going to be our answer. We need to start keeping track of that. At this point, I just need to be careful that there can be scenario where k is equal to n, right? In that case, by this time, j is already out of bound. J is equal to n. If j is equal to n, then I need to be careful, and I need to see that what happens at that point. So if j is here, then I am going to take, or suppose j is somewhere here, right? Then I am going to take the event time and the total number of meetings that I have in the meetings duration variable, and use that as a free duration, use that to maximize the free duration, right? So free duration is going to be event time minus meeting duration. Else, what is the case? Well, I am somewhere here. This is the ith pointer, and somewhere, let me clear it up a bit. Right, I'm somewhere here. This is the ith pointer, and 1, 2, 3, 4. K is 4 in this case. So I am somewhere here, right? So this will be one ahead, right? So this will be here in representing this box. So I'm going to take the start time of whatever j is at minus the meeting duration. That's going to be my free duration. Start time at j minus meeting duration. Alright, now I'm going to shift both of them as long as j is less than n in this case. Get the meeting duration. I'm sorry, let me copy this. Increment it by, or decrement it, let's say, by end time of I, because we are shifting the ith pointer now, minus the start time of I, and also we are doing the increment on j, but this will be incremented, not decremented. At this point we need to be careful, because when I'm saying I is at this point, I is not really at this point. Actually, I is technically at this point, right? And what I've done right now is I have removed this meeting duration, that is this one. I've removed it from the window, and I have included this one in the window, right? So what I can say is I want to keep j at this point while keeping I at this point. So I want to shift j first and then get the answer. Why? Because at this point, I being at this point, I can just use this end time and jth starting time to get the window or the ideal gap that I am supposed to get. Otherwise, if I is at this point, then I don't have anything to get, right? The end time I can always do I minus 1, but then that will include the other edge cases, so I don't need to worry about that if I'm keeping I first at this point and shifting j, getting the answer, and then shifting I, right? So what I'm doing is I'm shifting j first, get the answer. At this point j can be out of bound, right? J can be n, so let's consider that case as well. Else do something else, right? So I'm taking the free duration, maximizing it, and eventually what is the maximization here? If j is out of bound, then we are going to do this maximization. There is no other case. Actually not this one. This time we need to include end time of I as well, right? I is in picture right now, so we are going to subtract the end time of I as well, which means yeah, this one, not this case for j, but this one represents the end time of I that we need to include in this particular case. Now the maximization otherwise will happen based on the start time of whatever j is at and the end time, right? So essentially the free duration is maximized against the start time of j, which is the greater value, end time of I, which is a smaller value, minus the meeting duration. Alright, now I am safe to increment I, because I don't anymore need this particular meeting, so I can increment. Return free duration. We don't need to worry about any out of bound cases right now because we have already worried about it inside the loop. So this is the sliding window approach to this problem. Let's see if this works. It does. Time complexity, since it's a sliding window, it's O of n, and space complexity seems to be O of 1, right? Alright, let's move to the third problem. Reschedule meetings for maximum free time part 2. Same problem as part question 2, just that we don't have k here. K is essentially fixed to 1. At most one meeting can be changed. And what is the change of the meeting this time? This time not just sliding, but just taking the window and putting it somewhere so we can reshuffle it. So I can take this and put it somewhere if we had space anywhere else. We have space here, we can move that here, but that's just called sliding, which we were doing it in the previous problem. Let's take some other example. I can take this window, change it to here if we have a ideal space for that particular box or meeting. Similarly, in this one, we can take this and shift it here, but that's not going to lead us to get the maximum space. So it's no point in doing that. We can shift it here, this one. So we have three possible three possible cases, right, for this to work out. And those three possible cases will be either slide it to this point, slide it to this point, or take this somewhere else in some other gap. Some other gap is very important here because it shouldn't be this gap. Only then it will mean taking a box and putting it somewhere. Otherwise, it will mean sliding itself, right? So we need to be careful. So first of all, we need to get the gaps, right? We can get that in a vector using start time and end time. How many gaps do we need? Do we need all the gaps? I don't think so. Reason being, we are going to get the any gap, right? If we are trying to maximize this, I don't need to worry about what gaps I have. I just need to worry about if there is a gap which is going to accommodate this one, right? So I can also take uh, gaps which are maximum, right? So as I try to get all the gaps, I can just take three of them. At most, three of them is going to be needed, and use that as the three gaps that I can compare against every other maximization that I'm going to do as I iterate, right? So uh, why just three? We are going to look at it. Let's just code, and we will understand more about it. All right. So I need to get three gaps, right? There are many ways to do it. I am going to take a min heap and keep putting the gaps inside that. For a gap, I also need few other cases or few other things to know which gap it belongs to, right? What I am going to do is I am going to take a vector, put the first element as the gap length, and the second element and third element as the starting and ending point. We can do it multiple ways. I'm going to do it this way. I'm going to take a min heap because I am going to see if the size of the min heap is going greater than 3, then I'm going to pop 1 and then keep continuing, right? So eventually I end up having 3 maximum gaps in the heap, right? So priority queue, I'm going to store a vector of int. So all right, let's get the size as usual. Um, if so, we need to worry about this gap as well, right? The gaps at edge cases. We can worry about it. Just check if the start time is something the first meeting is something greater than 0, then we can take it as a gap. Or let me write it like this: min heap dot push. It's a vector. The length of the gap is the start time itself. The starting point is 0 of the gap, and the ending point is start time itself. I'm sorry. All right. At this point, I don't need to worry about this. Is the first thing that will go. So min heap is going to have a size 1 if this is the case. So I don't need to worry about popping things right now. I can just start from the first meeting or the second meeting technically and start pushing the gaps based on the duration of the length of the gap. That is going to be start time of the current meeting minus the end time of the previous meeting, right? That's why we started with the first meeting, so that we don't need to worry about the edge cases. We worried about that here. So start time of the current meeting minus the end time of the previous meeting is going to be the length. Start time of this gap will be this particular, end time will be the starting time, and start time will be the ending time of the gap. So essentially I minus 1 is the start time, I is the end time of the gap. At this point I can check if main heap is, its size is going to be greater than 3, then main heap dot pop. And finally this gap, we need to worry about the last gap, which is not bounded by any meeting, so that is going to be main heap dot push. This time the ending time will be the event time itself, so that's going to be one factor in the length, and end time dot back, because that's the last meeting. So the start time of the gap will be the end time back, and the event time will be the end time of the gap, right? So orally it can be confusing, but if we look at it, it's not that difficult. So now I just need to do that again. At this point I can take these three min heap gaps and use it inside a vector, so that things are easier or convenient. Otherwise you will see how can that, or how can having heaps inside the iteration of the meetings to, when we will be maximizing and comparing it against the gaps, it can be a little difficult. So let's get the min heap gaps. As long as min heap is not empty, I am going to push the gaps in any order because it's not going to matter. I'm going to compare it anyways against all the gaps. It's just 3, so time complexity is not going to be any difficult. So first thing will be the length. The next thing will be the same order that we have. So I can just, instead of doing that, let's just min heap dot top, min heap dot pop. Finally, let's have an answer which we are going to maximize. At this point, we are going to just take the meeting, every meeting, and see if we can take this meeting and slide it to the left or right. If we slide it to the left or right, we are going to slide it within a lower bound and a upper bound, a hypothetical lower bound and upper bound, which is going to be decided by the previous meeting or the end meeting. If it's an edge case, then it's going to be decided the starting event time or the ending event time, right? So we can just do that, right? N I plus plus. So let's just have a upper bound. Every time for a meeting there will be upper bound. It's going to be either event time, right? If it's a edge case, else if it's not a edge case, if I is less than n minus 1, in that case the upper bound will be, it's going to be start time I plus 1. Alright. Similarly for lower bound, if it's an edge case, then it's going to be 0. If it's not, that is if I is greater than 0, in that case lower bound is going to be end time of previous meeting. At this point, let's also get the meeting duration for the current meeting. That's going to be end time of I minus start time of I. At this point, I'm going to check if I can slide to left or right. It's not going to matter if we slide it to the left or right. The answer is going to be same. That the gap is going to be the same. Just the position of the gap is going to be different, which is we don't need to worry about, right? What is going to be the gap? So gap will be basically maximization of answer. The gap will be the upper bound minus the lower bound minus the meeting duration. All right. Or take box away to some other gap. Let's capitalize other so that it's important. So for every gap that we have, check if the gap, so if it's some other gap, right? If this gap, uh, how should I? All right. So if I'm at this meeting, the some other gap will be this one, right? How I'm going to define that if it is some other gap, it can be some other gap previously as well. So I can say that if there is a gap whose upper bound is greater, so if the upper bound is greater than smaller than equal to this particular boundary or the gap, right? So what I'm saying is this is the gap that we need to worry about. My other gap should be somewhere here or here. So its upper bound of this particular meeting, upper bound of this meeting should be smaller than the lower bound of the current meeting that we have decided. I'm sorry about the handwriting. Similarly, the lower bound of this one should be greater than equal to the upper bound of this one, right? So what I'm saying is the upper bound of the gap or the lower bound of the gap. Let's look at the diagram again. The lower bound of the gap should be greater than equal to the upper bound. So it should be greater than equal to the upper bound, or the upper bound of the gap, that is this one, should be less than equal to the lower bound. Along with that, the duration of the gap should be greater as well, right? So gap of 0 should be greater than equal to the meet duration so that it can fit inside the gap. So answer is equal to maximum of answer comma, this time since we are taking the box away to some other gap, the lower bound and upper bound is going to be the length of this duration. Upper bound minus lower bound, right? At this point, actually at this point we can return the answer, right? Okay, some problem. This should be a for loop. This should be a push, not a push back. Okay, there should be event time. Alright, I hope there is no other mistake. Alright, works. Time complexity wise, just 3 gaps, so we don't need to worry about that. This is also not going to be mattered, or this one is just O of n. So technically it's just O of n if I'm not wrong. and space complexity is going to be uh, I guess O of 1, because this is just going to have 3 gaps. We don't need to have more than 3 gaps. So it's going to be log 3, log 3, so that's not going to matter in terms of space and time. So O of n and O of 1 is what I think. Alright, thanks.